Time to get started on our Unit 2 practice test. Let's go over a few things that you should already know, but just to be sure, remember these must all be handwritten, of course, showing all your work. If you're writing an explanation, that's okay to type out, but math work should be handwritten, and of course, an answer must be turned in also as one Word or PDF document, not several individual JPEGs or Word docs. Pictures, of course, must be clear enough so I can follow your work. So make sure you take a nice, clear picture and look at it before submitting. Of course, questions here are similar to the unit test, very, very similar. And that's why this is the best tool to use as you take the unit test. So have it in front of you, let it be your guide, and name your file as you see below. As far as points goes, this is worth 10 points just for taking notes. There is a part 1 test, 12 questions, 3 points each for a total of 36 points. For this unit, there is also a part 2 test, which is 27 points. That is a teacher graded assignment, meaning I will be grading it, and we're not going to look at that during this video. We're going to look at numbers 1 through 6. But rest assured, there's nothing on part 2 that you haven't done before. So if you understand the quizzes and the content we've learned through this unit and this review, you will be set for that as well. Don't forget, all part 1 tests may only be taken one time. You can take your time with that and revisit it if you need to. Take your time, no retakes, but part 2 can be retaken once and only once, but you have to earn full credit for the practice test. With that said, let's look at number 1. We're going to go through 1 through 6 today and 7 through 12 next time. Given the functions f of x and g of x, describe the transformations of the graph of function f onto the graph of function g. That is worded a little bit strangely. What it's really saying is, if you look at function f first, and then look at function g, what's changing? Well, let's look at our functions and we can clearly point out the differences. First difference, I see a -1 next to x, where here I see a +2. That is dishonest h. That means there was a horizontal movement from +1 to -2. Remember, h is dishonest, so it's the opposite sign of what you see. Now, if you visualize that on a graph, what that actually means is if we move left from 1 to -2, there was a horizontal shift 3 units left. Okay, that's the first change that happens. But there's also a +1 here and a +4 there. That is elevator V, moving from 1 to 4. So that means our elevator moved up 3 units, and up is a vertical shift. Number 2. What are the coordinates of the hole in the graph of f of x? So they're telling you there is a hole. You're not always told. So that's helpful. And here's how we find it. First, we need to find out what makes the denominator equal to 0. So we set it equal to 0, x plus 4 set equal to 0, and solve for x. So we get x equals -4. So at this point, we know -4 will make the denominator 0 if we plugged it in for x. But we don't yet know if it will make the numerator 0 as well. And remember, that's how you know where a hole is. Anytime you get a fraction 0 over 0, there is a hole that you need to find. Okay, so let's plug in that x value we found, -4, into the original function and see what happens. You square, you subtract, you add, and you do get the 0 over 0, okay, which is undefined, right? Now, this is different than what we're used to. This is a very special circumstance, right? Because usually in a function, if you put a value in, you get a value out, right? And if you don't, it's undefined. Okay, I guess there's no graph there. But the 0 over 0 fraction is a specific indicator that there's a hole in your graph. So what do? We take our original function and simplify it. And how do we simplify? Can we just say, okay, well, 4 goes into 4 once, so 1, and 4 goes into 16 4 times, all good, right? And then x goes into x once, x, right? No, we're not going to do that because you can only cancel out factors, okay? These are not factors, so we need to factor it to then hopefully cancel some like factors out, okay? So what do? We look at what we have. The denominator is as simple as can be. No factoring patterns there. But the numerator has a difference of squares. These are both perfect squares, and they're being subtracted. Hopefully you remember from before the difference of squares pattern. It's right there in case you forgot. And let's use it. Okay? This basically says if you have two perfect squares being subtracted, you can write your factors like this. So we know there will be a minus and a plus. We see that below. But what is A and B? Well, let's think about it. In this case, A squared, what's in place of A squared? X squared, right? That's the first term. And what's in place of B squared? 16. I didn't mean to circle the negative. We're leaving the negative out of this. There we go. So B squared is 16. We want A and B, not A squared and B squared. So how can we turn A squared and B squared into A and B? Inverse operations, right? Square root, whatever you do to one side, do to both. So A is X and B is 4. This was a 16. So we just plug that in everywhere we see in our pattern. And that's exactly what we have here. Great. Numerator is factored. And lucky for us, that cancels out because that is also the factor in the denominator. Beautiful. So now we have this cute little function. We like cute little functions, don't we? Because they make our lives easier. Okay, at this point, finally, we can substitute that x value we found for the hole back into this function to find the y value of the point on the graph where the hole is. Okay, so we find the y value of -8. So our hole is at -4, -8. We have answered the question. And if you were thinking about graphing this visually, okay, y-intercept would be -4 and slope would be 1 over 1. So we'd have something like this. Y-intercept is 4. I don't need to draw the whole graph. My point is, I want to remind you what a hole on a graph looks like. It looks like this. Okay, and we found that is at -4, -8. But what's the significance of a hole? What does it actually mean if there is a hole? Well, it means that specific point is not a solution, right? Because didn't we say earlier that you get 0 over 0? Anything over 0, it doesn't matter if it's 0 or x or 1,000, it is undefined. So at that point, this function is undefined, and that's why there's a hole right there. Number 3. What is the graph of the function? Explain your reasoning. Okay, make sure you show work or provide an explanation. I've provided some brief explanations on the left, and we're going to use some process of elimination to guide us through. Okay, so we're matching the graph to the function. So what kind of function is this? Hopefully you remember that it's a piecewise function because we have several different pieces and they have rules which chops them up a bit. We see that in each graph example we have. Okay, so what are we going to do? There's so much information in this piecewise function. Well, let's take it one step at a time. X plus 1. Okay, can you graph x plus 1? Yeah, right? If you graph that, you're going to have a y-intercept of 1 and a slope of, well, coefficient of x is 1, so slope of 1 over 1. So you're going to have this line like this, right? That extends all the way to here. Well, that would be if there was no rule, but there is, right? We're saying the rule is if x is less than or equal to -2. So let me explain how I like to think of this. I like to think of this as the line x plus 1 exists only where you have x values less than or equal to -2. So that's why we cut off all the parts of the line with x values that are greater than -2. And because of that or equals sign, do you know what changes on the graph? It's that solid dot, right? Because -2 is included. It's part of the solution set. Okay, so we know this line is accurate. So where else do we see that? We see it here and up. D is out. Process of elimination. There we go. All right, time to handle the second part of this, which is starting with this function, x squared. That is the parent function of a parabola. It's a quadratic. Okay, parabola is this curved line. We know the parent function has the vertex at the origin. And we see the line where x values are between -2 and +2. Well, -2 is there, +2 is there. That line is between there. And because it's not or equal to, we have our open dots. Now, I know that's the case for all three graphs. So you might be wondering, Mr. T, why do we need to go over this? They all look the same. Well, because this is still important to know. Graphs are not always going to be so simple where everything looks the same. So you need to know how it works and why it works. Okay? So nothing eliminated, but we've just confirmed that this parabola is looking good for all three graphs. So the last one is really going to knock some things out. Okay, let's see what it is. We have this. What kind of line is that? What do you know about -1/2 x on a graph? Well, think about slope-intercept form, right? Y equals mx plus b. What's attached to x? M, which is the slope, okay? So we're looking for a straight line with a slope of -1/2, and what would the y-intercept be? Well, you don't see anything there, so it's the origin. And I'm just going to pick this graph. Origin there, slope of -1/2. So negative rises down, down 1, right 2, down 1, right 2. So we know we would have this line, but only if or where x values are greater than 2. Okay? So let's take a look at these lines. We're looking for x values greater than 2. Yes. Yes. And yes. All three of these have x values greater than 2, but what about the line? What about it? It's negative. It has a negative slope, right? So B is out. That clearly does not have a negative slope. So it's between A and C. What's the difference? The only difference is the open dot or solid dot, and this is not or equal to, so 2 should be an open dot, meaning our answer is A. Numero quattro. Answer and explain. There are three parts to this. A. What is the vertex of the graph of this function? What kind of function is this? Hopefully you notice it's a quadratic. If you multiplied this out, you would find that. What form is it in? Vertex form, which, surprise, surprise, specializes in finding the vertex. So what is the vertex? The vertex, I'm actually going to write that out because that's a little confusing. The vertex is h comma v. So whatever dishonest h and elevator v are, we put it in parentheses, and that's our vertex. Remember, h is dishonest, so positive 3, and then minus 4. Easy peasy, that's it. That's your vertex. B, find the x-intercepts of the graph of this function. Again, what type of function is it? It's another quadratic. Highest power of x is 2. Quadratic. And what form is this in? Standard form. Does standard form specialize in finding the x-intercepts? No, it specializes in finding the y-intercepts because think about this. Y-intercepts happen when x is 0. Well, if all of these x's were 0, nothing would be left but the minus 3. So this specializes in finding the y-intercepts, meaning we need to do a bit of factoring to get this in factored form so we can find exactly what we're being asked to find. This is a quadratic leading coefficient of 1. So the x method will factor this completely. Okay, we use our x, we put a times c on top, b on bottom. And we need to find two numbers that multiply to give us the top and add to give us the bottom. In this case, that will be -1 and 3. Okay, so you always set up your parentheses with your x on the left. So all of these underlined parts are a given. And then you just put in the values you have. It doesn't really matter the order. You could put -1 and then 3, 3 and -1. As long as you have them both, you're in business. And at this point, we were very close to finding those x-intercepts. Okay, we're going to use the zero product property and set this entire thing equal to 0. And zero product property says if this equals 0, then this whole thing equals 0, making this a true statement. So that's why, and vice versa. If this equals 0, the whole thing equals 0, making this a true statement. So we set each factor equal to 0, like we do here and here. Solve for x. So you have your two x-intercepts. Okay, technically an x-intercept is a point on the graph. We already know that y is always 0. Depending on the quiz or the test, you might be asked just for the x value or the entire point, but we have both. Why not? And the last part of number 4, find the x-intercepts. We're being asked to do the same thing, but different function. And man, this is a nice one because it's already factored, right? We get to skip all of this and just go straight to setting each factor equal to 0. This one's 1 and done. This, just add 1 to both sides. There are your two x-intercepts. Number 5. Not too much going on here. What are the equations of the asymptotes of this function? Okay, remember, a vertical asymptote looks like this. Vertical asymptote, and it always starts with x equals the equation of the line, right? The equation of a horizontal asymptote always starts with y equals. Okay, and what does it equal? Well, it's going to equal h, whatever h is in our function. Okay, and the horizontal will equal v, whatever elevator v is in our function. So let's start with h. Looking at our function, we see dishonest h hanging out with x as normal, and dishonest means opposite. So since h is -3, the vertical asymptote is at the line x equals -3. And the horizontal, well, that goes with elevator v. So -5 doesn't get much simpler than that. V is -5, so the equation of the line is y equals -5. That's our horizontal asymptote. And one more thing to think about. -3 would make the denominator 0, right? So hopefully you have at least a moment's thought of, is this a whole? Well, let's look at the numerator. We have 7, okay? And all we can really do with this function, other than graph it, is plug in x values and see what comes out of it. So is there any x value in the world we could put in that would ever make that 7 a 0? No. It's a 7. It will always be a 7. It's a confident young lady. And 7 is 7. Nothing's going to change. So there is no hole, but there is a vertical and horizontal asymptote. One more thing to think about. We saw holes recently. Even though there's no hole here, do holes and asymptotes have something in common? They do, right? They are all red zone restrictions. They are all places your graph line can never touch or cross. And finally, number 6. Graph this function on the interval -3, 3. What type of function is this? I'm just going to have you go through this. We went through a lesson on this very recently, 2.10. So I'm going to ask you to go through this and try your best. Pause this so you can practice. And now we're going to see how you did. This is a step function. It is not an absolute value function, right? You see these little feet, little minion feet on the bottom. That means it's a step function, but not just any step function. It's a floor step function because the feet are on the floor. And we also call that a greatest step function. Okay. And where is the most important point to plot first? It's always a solid dot at the origin. So when we do that, when we plot a solid dot at the origin, that is part of the first step of the parent function, not our transform function. But we use that to guide us as transformations happen. You're going to see what I'm talking about right now. Greatest floor function, does that mean this line goes over to the right from the origin or the left? The way I like to remember it is least left. A little alliteration to maybe help you. Least left, so then greatest must be to the right. Okay, so that is the first step of the parent function. But we don't want to graph the parent function, right? We want this function, and there is only one transformation, that plus one, which is elevator V, meaning there's a vertical shift 1 unit up. So what's going to happen? This step will move up there, okay? So at this point, the only thing, let me get that segment back. At this point, the only thing we would have graphed is this, because you'd use that parent function to help you get started, and then you would erase it. And since no other transformations were made, we know every step is one length, 1 unit long, and 1 unit above or below the other. So up one, over one, up one, over one, down one, over one, down one, over one. And we don't do this forever, right? We don't go up into the clouds, a graph to 1,000,000,000. We end at -3 and +3. Remember, that's what on the interval or over the interval means. We see that indicated with those red dashed lines. So we only want the step function between the x values of -3 and +3. And with that said, we're done with the first half of the Unit 2 practice test. Rewind, pause, fast forward, take notes, study, and you're going to do very well. See you next time.